Good afternoon, ladies and gentlemen. I'm Samuel Arias, and I will present an abstract of my work entitled Distribution of Cup Sections in the Hilbert Modular Orbifold. I've divided this presentation in 4 steps, beginning with an abstract, then settings, main results, and the classical case of the modular orbifold. Let K be an algebraic number field. Let M be the Hilbert modular orbifold of the algebraic number field K, and let MQ be the probability measure uniformly supported on the cos cross sections of the Hilbert modular orbifold at height Q. We generalize a method of Sayé and show that MQ distributes uniformly with respect to the normalized hyperbolic measure M on the Hilbert modular orbifold as Q tends to 0, and relate the rate by which MQ approaches M to the Riemann hypothesis for the Dedekind zeta function of the algebraic number field K. The settings then are the following. We need an algebraic number field K of degree n. This degree is written as R1 plus 2R2, where R1 is the number of real places and R2 the number of complex places. We also have a ring of integers O and a Riemannian manifold or symmetric space formed by a product of R1 hyperbolic planes and R2 hyperbolic spaces. We also have the Hilbert modular group that acts properly and discontinuously on this symmetric space by a formula related to the Mobius transformation. If the field K has class number H, then the Hilbert modular orbifold has H cost, and each cost can be parameterized by the standard cost at infinity. Therefore, we have an orbifold which has a finite number of ends or cost. This cost has associated transversal sections parameterized by their volume. In other words, from the geometry of the Hilbert modular orbifold, it follows that for each cost and each real number Q bigger than 0, there exists a generalized closed holosphere of codimension 1 that are related to the closed holocycles in the case of the classical modular orbifold. Then we can define probability measures uniformly supported on the transversal section when we see the Riemannian metric on the transversal section that is inherent from the ambient space. So we sum up all these transversal measure or normalize it also to be a hyperbolic probability measure, and we also consider the normalized hyperbolic measure of the Hilbert modular orbifold. The main result of this work tells us that the measures MQ are uniformly distributed with respect to the measure M as Q tends to 0. And this tells us that when the volume of the transversal manifold started to increase, then this manifold start to cover the whole Hilbert modular orbifold. And we obtain a picture like this, where we see some submanifolds of codimension 1 covering the whole Hilbert modular orbifold. We also give a generalization of Sayé's equivalence to the Riemann hypothesis and prove the following assertion. The Riemann hypothesis for the Dedekind zeta function of K holds if and only if for every smooth function f with compact support on M, one has the following relation, which tells that the rate of approach of MQ to M can be at certain speed, or can be improved to have certain speed if and only if the Riemann hypothesis for the Dedekind zeta function of the field is true. Finally, we will illustrate the case of the classical modular orbifold, and we begin with a picture of the Dedekind tessellation in the hyperbolic plane, which has as a quotient the classical modular orbifold, and this orbifold has a family of closed orocycles parameterized by the real line, and we see that when these orocycles get larger, they start to unroll over the classical modular orbifold, and finally when the length of this closed orocycle gets large, it covers uniformly the classical modular orbifold. This is related to the Riemann hypothesis, which is also related with the prime numbers that I have pictured here using MAH numbers. We can see a simulation in the case of the hyperbolic plane in this direction. Finally, I want to thank Professor Alberto Berhovsky-Solá for suggesting Zagier distribution theorem in the case of the Hilbert modular orbifold, and for all his great explanation in this remarkable subject. I'm Samuel Estala, thank you very much, and see you later.